So take note a lot about parametric and non-parametric tests. Parametric is the mean, non-parametric is the median. Parametric is normally distributed data. Non-parametric is unskewed data. Parametric deals with ratio or interval. Non-parametric deals with ordinal or nominal. Okay. I'm not really teaching deeply. I'm only lecturing, so kindly take note. So what I'm going to do now is that you can look at one sample. Okay, for example, you can take the ages of students in a class, and everybody will mention the age. So you have just one sample, and then you can check whether the one sample is equivalent to a hypothesized mean. In that case, the test statistic you're dealing with is a one sample test, if the data is normally distributed, or you are dealing with a binomial test, or Kolmogorov's-Smirnov test, if the data is skewed. So take note of that. Now, you can also take the same ages in the class. By this time, you separate that of the male age from the female age. Get a point. You're comparing the male, their ages with that of the female. Maybe you believe that the males are older on average than the females. Maybe you believe that there is no significant difference in the ages. In that case, the sample, you got to know what sample you are dealing with. Because the subjects are male and the other subjects are female, these subjects are separate from each other. So we say the sample is independent. In that case, if the data is normally distributed, you will use an independent t-test. But if the data is normally distributed, use an independent t-test. If the data is skewed or non-normally distributed, you use a Mann-Whitney U-test or a Wilcoxon rank sample test. We're going to do these ones. But before we do any of those, I just want you to know the key purpose of hypothesis testing. The hypothesis testing is usually the fact that there is a statement, a populative statement, and you want to compare what you believe based on your research against the populative statement. So there is a null hypothesis. Whenever you're doing a hypothesis testing, there is always a null hypothesis, and there is an alternative hypothesis. And the null hypothesis is the authoritative statement. The alternative is the mirror image of the null, which you are intending to reject. So usually, when you reject the null hypothesis, what you are saying is that you are going in favor of the alternative. Okay. But what will make you reject the null hypothesis? Well, that is, I've told you this already the other time. That is if your p-value is less than or equal to the level of significance. So if your p-value is small, that means you made actual errors were smaller than the expected error. So this is more or less like the actual error, the p-value, and then the level of significance, the alpha, is the expected error. And so your hope is that your actual mistake is lower than the expected mistake. In that case, you have enough gravitas to reject the null hypothesis. Okay. That's it. I hope you get it. So we are going to take some couple of examples to check. But when I give you the data set, what I want you to do is to check whether you are going to use parametric or non-parametric. Because something in the data set should guide your thinking process as to whether it's parametric or non-parametric. So let's check the MPG. Do you remember the MPG? The MPG data set. If you can remember, there was one of the columns which is automatic versus manual. So I want you to go to your RStudio and open the MT-CARS data set. So just go to your RStudio. I'm showing my MT-CARS. Please check if you can see my data set. So go to your desktop and just run MT-CARS. I am just doing mine in the command. I hope you can see it. Can you see the MT-CARS?
Yes.
Yes, please.
Yes.
So
please.
once you show that, you run it. And I just run it. When you look at the bottom, you will see the data set loading. Now the column I'm going to be dealing with is the AM, the column AM, automatic and then manual. Automatic and then manual. So you must have the hypothesis clear in your head. What are we checking? Well, we want to check whether there is a significant difference in the MPG, the mass per gallon, okay, between automatic cars and manual cars. In other words, if I look at the MPG of automatic cars and I look at the MPG of manual cars, and I calculate, for example, the mean. Now, why will I calculate the mean? Because I must believe that the data is normally distributed for me to calculate the mean. Okay, so let's assume that the data is normally distributed. However, do you remember that the last time we looked at the data, we realized that the data was not normally distributed? Do you remember that? I hope you do. Okay. The data was not normally distributed. Now let's make an assumption that the data is normally distributed. All right. Then we check whether automatic cars outperform manual cars. That's what you want to check. In other words, do you believe that automatic cars significantly, the moment the word significantly comes in, it means that you are doing a statistical testing. Whether automatic cars significantly outperform manual cars. That's what you want to check. And when you look at the data set, you will notice from the data set, look at the column, that 1 and then 0. 1 stands for manual. Okay. So anytime you see this 1 at the bottom here, it's manual. 1 is manual. So you can see that the first car, Mazda, has the manual. It's a manual car. The second one, Mazda RX-4, that one is also a manual car. The Datsun is a manual car. The Hornet 4 Drive is also an automatic car because it has a value of 0. Okay, so that's what you want to do. Now, to be able to check which manual or automatic car outperforms the other, you want to check your data to be sure whether the data shows some difference before you come and state your null and alternative hypothesis. So there are 2 things you can check. You can check whether there is a bit of disparity between the data set. So how do you do that? Now, we don't want to be typing $something. We don't want to be typing that. So we want to attach the data set to the memory of R. How do you do that? So type attach. Just type attach. Remember that later on you have to come and detach. So you attach MT-CARS. That's what you want to do. And like I said, so do the attach and then run it. And when the cursor go to number 2, the next command, just type detach, but don't run detach. Okay. The detach here means that we are removing the MT-CARS from the memory of the R, but we don't want to run it here. When you're leaving the computer, you're done with everything. That's when you do the detach. So I have run the attach. You can see that at the bottom in the console. So the attach is on. So you now go to the next command. Okay. And please go and find out why I did attach. I've explained it, but go and find out. We want to print every data information in the MT-CARS into the memory of R so that we don't reference the data set anytime we are looking at it. So we can check whether the data set is normally distributed. And like I told you the last time, we did check that. Okay. But for now, we are doing for groups, automatic cars and manual cars. So I'm going to take one plot and just compare the two, automatic cars and manual. How do you do that? So just type box plot. We just want to generate a box plot between the two. So type box plot into bracket, the data set, the comparison factor, the MPG. So type MPG, and then bring your tilde sign. The tilde sign is like S turned horizontal. Okay. So bring that tilde sign, and then the comparison difference that we are looking for is the automatic and manual. So when you look here at the bottom, the automatic and manual, what name have they given to it? They've given it a name AM. AM. And so you're going to type that AM. So you have MPG, which is the dependent on the automatic or manual cars. After that, you can bring a comma and give a title of your graph you're about to draw. So bring a comma, type main. That is the title of the graph I'm doing. And just type MPG, bring apostrophe first. Type MPG grouped by AM. Grouped by AM, that is grouped by automatic manual. That's just the title. After that, step out of the double apostrophe and bring a comma. You can use colors. Okay. So let's name the x-axis. The x-axis is a type of automatic or manual cars. Okay. So let's name the x-axis. Let's call it X label. X label, and bring double apostrophe, and let's call it a type of AM. That is type of automatic or manual cars. And then step out of the double apostrophe and write X, Y label. So let's label the Y as well. And the Y, remember we are drawing the box plot. The Y is the miles per gallon. Okay. So let's type the Y and call it miles per gallon. Okay, that's it. And then let's give a color for the box plot. So do a comma and type COL, that is a color, equal to, and then into a double apostrophe, give it color, any color. I am giving it blue. Somebody should give it color green. Someone should give it color red. Someone should give it color gray. Someone should give it color yellow, and any other color that you want to use. Sometimes we keep it simple by giving them primary colors. So I'm going to run this, and then hopefully you see the graph. Let's run that. And you can see that the graph is showing in my case here. I'm going to interpret the score for you to have a feel of it. Let me see, those of you who are been able to do it, let me see by hands. Let me see which of you have been able to generate this box plot. All right, good. Kenneth, quite a good number. I like it when people are following me. Okay, Felix, okay. I like it. I like it a lot when some are seriously following me rigidly. Seriously following me rigidly. All right. So now I want you to look at the graph, which I have done also here. And remember, the manual is the number 1, the automatic is the number 0. Okay. The manual is the number 1, the automatic is the number 0. And please try and always wear a dress when you join a Zoom. Now, number 0 is automatic. If you look at the black line inside the blue, that black line is the average. Okay, that is a mean, okay, or a median of the distribution. The 75th percentile is the one at the top there. Let me try and see if I can use this to show. That is a 75th percentile. I hope my screen is not going to. All right. So that is 75th percentile, and then the 25th percentile at the bottom there. And so you have the 75th percentile of the box just at the end of the blue, and then the 25th percentile is at the middle. And then the median, which is the 50th percentile, is in the middle. Now, just focus on the average. If you look at the average for the automatic, which is 0, it is below the average of the manual. Okay, if you look at the average of the manual is about 23 miles per gallon. And then the average of the automatic is about 17 miles per gallon. So you can see that in reality, it appears that automatic cars are performing better than manual cars. You can only say that, but you can't say that they are statistically significant in their performance. Okay, we are yet to prove that. Okay, so that is the, someone has privately chatted me that getting the tilde sign is a problem. The tilde sign is under the escape key. But again, depending on the kind of computer you have bought, if you bought an Asian computer, it might be different from if you bought an American or British computer. But the tilde sign is under the escape key. It is that S turned horizontal. So now you take this picture and you take it to your word, and then you can now say that there is a difference. But again, you got to prove this statistically. So that is what leaves us with our next thing that we are going to do. So you've shown graphically that there is a difference. Okay, so you've been able to prove that there is a difference. And you remember that you're able to spot whether they are outliers. One thing about box plots is that box plots are able to help you to identify the outliers. Okay. Now we can proceed. What tests are we going to test? What statistical test? We are going to use parametric or non-parametric tests. Which one are we using? Well, from your analysis, okay, because we assume the data is normally distributed, we are going to use parametric test. Now, after you've chosen the test, the next thing is the data sample dependent or independent? Who can tell me? Is a sample dependent or independent?
Independent.
Explain. Explain why you say it's independent. Because that answer you gave is a lottery answer. Anybody can give the answer. I gave you just two options, so you can guess.
I think it's independent because the automatic cars does not affect the manual cars. They are independent on their own. I mean, a car is either automatic or it's manual.
Okay. Who else has some answer? The independence is as a result of the fact that the subjects are different. The subjects, the cars that are automatic are different from the cars that are manual. if it was a dependent sample, the same cars, you are recording something of them. That's what it means. It's like the same cars, okay, you are checking the miles per gallon before something, before a race or after a race. Okay, so in this case, it's the same car, but you are checking that same car, its situation before and its situation after. So dependent samples are samples that are matched, samples that are paired. But independent are unmatched, unpaired. All right. So now that we know that we are going to deal with dependent sample, let's start by, please note also that you can also run your kernel density estimation to see the distribution. And you can do that on your own. It's in the slides, so check it. You can do kernel density estimation. So let's start our test. How do you do the tests? The first thing you do, we are going to do t-test. So just type t, okay. Because we are doing t-test, just type t dot test. T dot test. Then you put into bracket mpg with a tilde sign, and then you write AM, that is automatic manual. You are using the column, that same column that we are picking the information from AM. Okay. So that's it. That's it. That's a test. That's a test statistic that you're going to use. Now, this test is a t-test, so we know it's parametric, but it doesn't tell us whether it's a one-tail test or a two-tail test. Now, for your information, a two-tail test is always stronger, okay, unless there is an extenuating circumstance you want to use a one-tail. So what I'm going to do is I'm going to indicate the test structure to let you know that it's a two-tail test or it's a one-tail test. So one thing that you can do is that you can type, after the AM, you can type alternative, then equal to, and then you write less. You step out of the double apostrophe and then indicate that the variances are equal. Because one of the assumptions of parametric tests is that the variances must be equal. So you write variance dot equal is equal to capital T to indicate true. So watch something here. If you want to indicate that, this is a one, what do you call it? This is a one-tail test. You bring this information alternative less. Okay. If you believe that you don't need a one-tail test, you need a normal two-tail test, you don't bring this, you can cut off that. You can cut off that alternative less. So we are doing two-tailed, so I'm just cutting off the alternative and just run it. Run this. And look at the bottom, and you'll see in the bottom some beautiful information. Okay. Let me see those who have been able to do it. So this is a two-tailed test. You can give an instruction, bring us a hash symbol and just write, this is a two-tailed test. Let me see, I just want to be sure that at least one person have been able to do that with me. I'm taking notes of this and I'm taking marks as well. Please take notes. Who has been able to run this and who has encountered a challenge? Yes, Kenneth. You encountered a challenge?
Hey, Doc, please, I think you typed Tilton or something like that.
That's what you are trying to correct.
Yes, but I think I've been able to run it with it.
Are you the one who raised your hand?
No.
All right, James.
Yes, Doc, I've been able to do it.
All right, okay. So now look at the results down there.
Hello,
What
I've
is,
also been able.
what is a test statistic? What is a test statistic that you see there?
It's minus
Minus 4.1.
1061.
Okay. So normally
The
you
difference
would
of
take the absolute value of this. So the test statistic is 4.11 approximately. And the degrees of freedom is 30, which means that your independent variables, what do you call it? You've got a degrees of freedom of 30, which means that you have the sample size minus 2 in this context. Okay. Because it's above 30, and so it's more or less entering into the Z zone. But if it is below 30, then the sample size is small, so your degrees of freedom will be n minus 1. Okay. All right. The most important thing you are focusing on is the p-value. P-value. And please always mute yourself unless you have a question. Okay, p-value. If you look at the p-value is approximately 0, which means that your error that you made, your actual error that you made is approximately 0. Okay. Therefore, because your p-value is less than the level of significance, you now have enough gravitas to reject the null hypothesis. First of all, what is a null hypothesis? Who can tell me what the null hypothesis is? We didn't actually write a hypothesis, but you should know. What is a null saying? Okay. The null is saying that there is no significant difference. That's what the null is saying. See? Let me write it here. The null is saying that, okay, that no significant difference in the MPG of automatic cars and manual cars. Okay, so that's what the null is saying. The null, that's what it is saying. Now, what is the alternative saying? The alternative is saying that there is a significant difference. Okay. In other words, one is outperforming the other, and the other is underperforming one. Okay. So the alternative is saying that there is a difference. The null is saying that there is no difference. And now your p-value is 0. It's less than the level of significance. So you reject the null hypothesis, which says there is no difference. You reject the null hypothesis and conclude that there is a difference. Okay, now there is a difference. We know there is a difference, but the difference is in favor of who? In order to know which one it is in favor of, look at the bottom and always come and check the groups. Remember, automatic is 0. Remember that automatic is 0. Automatic is 0 here. Manual is 1. And if you look at the automatic, the mean is 17. And if you look at the manual, the mean is averagely 24.39. Just like the box plot was trying to show you. So you can see that the manual has a higher mean than the automatic. Okay, so now you can see numerically which one is performing better. You know one is performing better, but the software is telling you that the manual is outperforming the automatic, statistically and significantly speaking. Why do you say statistically and significantly? Because you've tested it. You just did a test. Okay, so you can now say that, in conclusion, you're going to say that since the p-value of 0, okay, is less than the level of significance of 5%, we reject the null hypothesis at the 5% level of significance and conclude that the MPG of automatic cars outperform the MPG of, the MPG of manual cars outperform, and the moment you write manual cars, put the mean there. The MPG of manual cars into bracket 24.39 outperform the MPG of automatic cars into bracket 17.15. Yes, Felix.
Doc, why is it that we are using 95% instead of 99%? Because I was thinking this one is, the p-value is close to 0.
Oh, yes, you can use 99%. So once you use 95%, you can also use 99%. In this case, you can use 99% to make your judgment. There's no problem. If you go and run the percentage, the level of percentage, it will give you the same p-value, the same 0. So yes, there's no problem to say 99%, okay, and 95%. The thing is that it is when there's a challenge. It's when there's, you are getting a p-value which is smaller than you become conscious. But other than that, if you get a p-value bigger than 5%, that's when you start panicking. But anything else, you can say there is a 1%, error. You can say a 99% confidence interval in the result. And in fact, when you look at the result, you see that the 95% confidence interval is there. If you look at the -10 and then the -3, you can see that the t-value of -4 is in between. It falls within the confidence interval. But I thought that sometimes when I'm giving you these to explain, it can be a challenge for some people. So that's why I'm using the p-value to make it simple. That's it. You can do your conclusion. Now, what if this data was not normally distributed? Well, in short, if the data had not been normally distributed, you will have to not use the t-test. Okay. If the data was not normally distributed, you would have to not use the t-test. But what will you use? What are you going to use to prove your point? Okay. Well, then it means that you will have to use a non-parametric test instead of using a parametric test. You have to use a non-parametric test for that purpose. How do you go around that? You're going to do that. I'm going to use a certain data set. Okay. Let me see what I can get you a different data set for that purpose. Somebody has written some question. Let me see. Anybody, you say you ran into a challenge. What was your challenge? Anybody?
Yeah, Doc.
Yes.
Right from the box plots, I was unable to get the data from there. So I've been missing for a while.
Say that again.
I said right from the box plots, I was unable to get the data or the box plot correct. So since then, I've been following your screen. I have difficulties getting it on my own.
Okay, you mean you can't do it again? You are not following your own again?
Yes, please. Yes, please. That's the point.
Oh, that's a shame. Okay. Now, if this, let me just copy command that I have here. If I had copied this command and pasted here, if the data was a paired dependent sample, okay, if the data was a dependent sample, how would you have worked it? Please note, I just want to show you. Okay. The first one was independent, so I didn't bring something. But if the data set was paired or dependent, so that's another way, dependent, how will you have actually done your analysis. All you got to do is that bring a comma after this variance equality, the homogeneity. Bring a comma and just type paired equal to, okay, and then you add true in capital letters. So look at the command number 6 and the command number 5. The difference between the two is that if you believe that the data is dependent. Now, when do we mean the data is dependent? I'll give you an example. Suppose you want to check the MPG of cars, okay, of all these cars, before a certain time period. And then the same cars, you're also checking their MPG after a certain time period. Okay, that is when you will now have that situation that we are talking about. Okay, when you have that, what it means is that the data is paired or is dependent. So you add this command and then run it. I'm going to run it here. So in this case, what I'm running is not an independent t-test, but it's a dependent t-test. All right. Now, in this case that you see here, okay, the software is not allowing it to happen. The part of the reason why it's not allowing is because the data should be arranged as if they are paired. Okay, the data should be arranged in such a way that they are paired sample. Because if they are not paired, it doesn't make the data work. So my empty cars, the way I have my empty cars, I have it in such a way that they have to be arranged in that regard. So if I were to, I'm going to do another one. I'm going to do another one with you so that you see how this paired works. But I just want to be sure that you understand the difference between paired sample, that is dependent sample, and unpaired sample, that is independent sample. Do you get it? Let me share before I move on. Do you get the difference? You don't get the difference. Do you get it? Do you get a difference? Yeah,
Yes,
Mary.
Prof.
Mary, hand is up. You see, in a Zoom, I will not know you
I would,
unless you talk.
Doc, yes, please, if you can hear me now.
Yeah, go ahead.
Great. So I'm asking if you could repeat what you said about the dependent and independent samples.
Okay. All right, okay, I'm going to repeat. I'm going to repeat in just a second. I think I've jumped the slides. So the thing about dependent is that the data sets are together. Okay, they are together. They are together. So I'm trying to show some drawings here. It appears that it's not allowing me to do the drawing. Okay, let me see whether the whiteboard will allow me. No, the whiteboard is not. Okay, I need to use writing, text writing. The thing is going to go off. If it does, I have to come back. Can you guys hear me?
Sure, Doc.
No, we missed you for a moment there.
Okay, like I indicated, going to go off. That's how sometimes the Zoom works when I'm doing on screen something. If it goes off, I have to come on again. So that is a difference between, that is a paired sample, okay? That's a dependent sample. Now let's go to the independent sample. The independent sample is not the same sample having the same subject having different samples, no. So this time, I'd rather have the MPG, one MPG, not two different MPG. I have one MPG, but I have the MPG of A, of B, of C, okay, and I have 35, 37, 38, you know, and then these cars are automatic. So because they're automatic, I'll say auto. I will say auto. I will say auto. Okay. And then the MPG for D, E, F, and G, they also have some numbers here, but they are manual. They are manual. They are manual. They are manual. But when you look at the MPG information I'm having, the MPG information I'm having is just one. The sample is just one. A is having only one sample of MPG. But unlike the previous one, A was having two samples. So the sample here on the right here is called independent sample, because the sample, independent sample, because the subject is only one. And the sample is also only one. But when you go to dependent sample, the subject is only one, but the samples are two samples or three samples. Does that make sense?
Yes, please.
So that is it. That is how you handle that. So if you believe that the samples are dependent, you indicate. If you believe that they are not independent, that one too, you indicate. All right. So I gave you a data set. I'm clearing this. I gave you a data set, and we're going to use that data set to look at the next information. And the data set was HSB2. Check it. HSB2. Let me see if I can show you the data set. HSB2. If I show you the data set, the one I'm writing, the thing will come, but I need to still show you. So this is a data set. Confirm if you can see the data set, and then I'll tell you a little bit about the data set.
Mm-hmm.
You see it?
Yes, please.
Yes,
right.
please.
So this data set you guys are looking at, there is something interesting about the data. And what is that? When you look at the data, this data set is the scores that were obtained by some students. Okay. The scores were obtained. It's a data file, and the students are 200 students. They are from high school. And there are a bit of demographic information about these students, just to give you a feel of it. For example, when you pick the first student whose ID number is 70 on the far left, this student, is the student a male or a female? Well, as you can see, it's been coded as 0 or 1. When you look at the sheet at the bottom, there's a sheet called description. So go and check male and female. You will notice that the male is given a value of what? 0.
Of 0.
And the female is 1.
1, yeah.
Okay. So you are able to see, so when you go to the data set, you notice that the first person is what? A male or female?
A male.
It's a male.
A male. The second is what?
It's a female.
A female.
The third?
It's a male.
The fourth?
It's a male.
Okay.
Male.
Now, another information we have about them is their race. So go to the description and see what they said about race. It says 1 is Hispanic, 2 is Asian, 3 is African American, and 4 is white. So when you go to the data set, the first person, you will say, what is the race of that person?
Hispanic.
It's white.
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 Don't worry, because there are quite many, you couldn't remember. Okay. Now, the number 7th person I've highlighted. What is that person?
African American.
It's African American, number 3. Okay. Now, the next column is the socioeconomic status of the person. Socioeconomic. When you go to the description, 1 is a low socioeconomic status. 2 is a middle socioeconomic status. 3 is a high socioeconomic status. So when you look at the first person, what is that person's socioeconomic status?
Low.
Low.
What about the third person?
High.
High.
Okay. And so you can see now, even if you are not told what kind of variable, what kind of level of measurement or data type is the first one, the female, the race, and the socioeconomic status. First, let's start with the female. Is it categorical or numerical?
Yes, categorical.
What about the race?
Categorical.
Same.
What about socioeconomic status?
Same. Categorical.
Same.
Exactly. Okay. Now, what do you think will be read? By the way, that read is your reading score.
Numerical.
What about write?
Numeric.
That will be their
Numerical.
writing score.
Numerical.
What
Also
about
numerical.
mathematics score?
Same.
Numerical.
Science score?
Numerical.
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 Social studies score?
Numerical.
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 And then the program type. What do you think is their program type?
Categorical.
Categorical.
That's it.
This categorical.
Okay, so you are supposed to have a feel of the data all the time. Okay. That is the data set that you have at hand. Now we want to check something. And here is a question. We want to test whether the mean for write, the writing score for males and female, whether they were the same. I want to repeat that.
Hello, sir.
Yes. Who was calling? Okay. We want to check whether the writing score for the male.
Economic status numerical.
Who is talking a lot like that? Ebenezer, your hand has been up multiple times. What is it?
Please, I wanted to find out if the second column, the heading, is supposed to be gender or female.
It's female. That's what they chose. That is what the Excel, the people decide to call it. Okay. But what is important is not the heading. What is important is what is inside or below the heading. Okay, so you should, for now, it was a slight confusion, okay, but it doesn't matter. You should know that 0 is what? Is female. Sorry, 0 is male, and then 1 is female. Okay. All right, now we are going to check whether male and female, which of them outperform the other. Did the males outperform the female when it comes to writing score? Or the females outperform the males when it comes to the writing? In other words, is there a significant difference in the scores of male and the scores of female? That's what we want to do. But we are going to assume that the data set is not normally distributed. I want to repeat that. We are going to assume that the data set is not normally distributed. We are going to rather assume that the data is skewed. Okay, so take note.
What's the reason for this assumption?
Okay, the reason for this assumption is nothing. It's just that I want to demonstrate how you work with non-parametric data. How you work with the other tests, so that it's not all the time t-test. That's all. So that's the first thing. We're going to assume that the data is skewed. which means that we cannot use a parametric test. Do you agree with that?
Yes.
Good. So keep that in mind. Second, this sample, is it dependent or independent? What do you think? Is a sample dependent or is independent?
It's independent.
That's it. It's independent. So we have an independent sample. We have assumed the data is non-normally distributed. So what test are we going to use? The test is known as Wilcoxon rank sum test. Wilcoxon rank sum test. So let's go to our R. I'm going to give you a bit of a heading. To do that heading, I'll leave one line. And then we are going to do the data set. Now, first thing you want to do is to bring the data set into R. How do you do that? How do you bring the data set to R? Type this command. Let's call the data set letter B. Letter B. So let's call B is equal to, yes, Felix.
So please, do we have to detach the empty cast before we proceed?
No, but no, we don't have to because we are dealing with a different data set. But it's good you've mentioned it. So let's detach. Let's go and run the detach to just remove for now. So just go run detach. At the bottom, you see the same detach written, which means that it's not shown. And then, because I'm going to load a different data set. There's no problem. So the data set we are going to load, I'm going to bring the data in Excel, but I want to give R a command so that R will know the name we are calling that data set we are bringing. So we are going to use something we call a clipboard command. So just type B is equal to read dot delin into bracket double apostrophe clipboard. That's it. Watch spellings very carefully. Okay. So that's it. What does that mean? This means that we should go and copy the data and come and run this command. That's all. It doesn't mean we should go and copy the data and come and paste it. No, it means that we should go and copy the data and come and run this command. So let's go and copy the data. So our Excel data, this is it, as you can see in the sheet. Just Control A to highlight everything. Control A, that will highlight everything. Control C to copy. Yes, Felix. Felix, your hand is up.
Did you run the command you placed before going to copy?
No, I have not run the command. I've just typed it, but I've not run it.
Okay.
So now that we have copied the data, Control A to highlight, Control C to copy. Let's go to our R. So we go to our R, and then when you get to the R, the command is in command number 8, as you can see. I hope you can all see it. Now that the cursor is blinking at that command number 8, you can run it. Let me run it. I just ran it. And for you to know that it's run, come to the bottom. In the console, you see it written nicely blue. That shows the data has run. But you want to feel it, eh? You want to see that the data is actually there. Yes, Ni?
Please, do you have to paste the data before I run?
No, you don't paste at all. Never paste.
Data.
Just copy and come and run.
Okay, okay. Nice.
And once you just run, to be sure that the data is in the memory, is loaded, just highlight the name you gave to it, B. Highlight that one alone, and just run that alone. And once you do that, at the bottom, you can see the data is all showing. Remember, this is 200 observation. Okay. So it is showing me 80 something of the 200. So this is it. Okay, I'm scrolling down. Okay, so you can see all the headings are showing as it is. Everything is nicely shown there. All right. Now, we are going to check. You can see the right score. Yes, Benis.
So, Prof, assuming you've copied maybe a couple of things in your clipboard, and then you wanted to run maybe not the last one that you have immediately copied, but the last batch one that you have copied, is it possible to specially label it in the command, or you always have to go and copy the last one before you can run?
No, once you have given it a name, for example, the one I just posted, I gave it a name B. Once I've given it a name, if I go and do another one, call it KK. If I do a third one, I call it school. If I do a fourth one, I call it AMA. Whenever I want to see that data, I just have to go and highlight that one, and that's it. I'll run that one to see it. You see, okay, the data is not just there, it's there for you to use it. So anytime I'm ever going to use this data called B, I will have to refer to the name B before I work with it. I'll have to refer. For example, you see, under the box plot, I refer to a name in the data set MPG. Actually, I would have written MTCAS $MPG. And I would have written MTCAS $AM. So that I'm referring to the name of the data because it's in the memory. If I do that right now, it's there. The only reason why I didn't do that is that I didn't bring the name of the data is because I attached it. When you attached it, you affix it. So you don't have to refer to the data anytime you're writing. So the B, that is how I will do it. Okay. The B, I'm not going to affix it so that you see how you always have to refer to the name of the data. Let's say that I want to talk about a variable in the data. I will need to tell R the name, which is B, before I refer to the variable. Yes, Mary.
Doc, please, when she asked the question, I was a little distracted. I have the command in, okay, so I'm fine now. I'm fine. Thank you.
So now that
I didn't get the stage where, hello, sorry. I didn't
don't worry,
get
once you are fine, that's okay.
About after.
Once you are fine.
No, I wanted to get it again to understand because I did it again, but I didn't understand. You said when you do the delim and this one, the command, then what do you do to get the data? Do you run which one? That's what I want.
You go and copy the data in Excel. And when you come,
yes, please.
You put the cursor at that command number.
Yes, please.
And just click run at the top here. That's all.
Thank you.
Okay, and then it will start showing. So now that we have our data, now comes the question. Do you think that the males outperform the females when it comes to writing score, assuming the data is not normally distributed? So how do we do that? Well, because the data is not normally distributed, what we got to do is to use the Wilcoxon rank sum test. It's an independent sample. Again, that's all in the table that I gave you. If I want to, you can do, by the way, is that you can also do a box plot. Let's do a picture of the whole thing and see, box plot. So let's do a box plot first. Yes. Lower your hands if your question is answered. Yes, who has a question?
Prof, please, is the Wilcoxon the only available test you can do for the non-parametric sample?
No, there are several of them. And when I started, I showed the table of all the non-parametric tests.
Okay, Prof, thank you.
Yeah, the Wilcoxon is just one of them. Okay, and the Wilcoxon is for 2 samples that are independent. Remember, the name is Wilcoxon rank sum. There's another one known as Wilcoxon signed rank. The signed rank is when the data is dependent. The rank sum is when the data is independent. Of course, you forget about this, except when you are working with them. When you're working, you keep going to refer to them. then you'll get to know it. Okay, so I just want to do a box plot of the relationship between female score and male score. And when you actually check, you remember the Excel gave you the interpretation. The Excel said that the male are 0 and the female are 1. Okay, in case you remember. And that column was called female, if you can remember. It was called female to the extent that one guy was even confused. Why was it not called gender? Well, the data was not my data. And where I picked the data from, the person called it female. So because the person called it female, that is the same name that I am using. Yeah. So you indicate right. What is right? Right is the dependent variable in a normal regression. Right is what male and female have gotten a score of. Right is the one that has got a numerical variable. Then the female is the categorical variable. So you are checking, you are comparing a numerical variable among two classes of people, female and male and female. Okay. So this is a box plot. You can give it a heading, but I'm not going to give it a heading, okay, just like the one above. Okay. We can also have the X label, the Y label, the color. I'm not going to give all of this. I'm just going to indicate the color because of time, because we've done a similar one already above. So color, let's call it green this time instead of blue. And just show the plot. Okay, I'm told female is not found. Let me be sure. Okay, so this is why you have to indicate which when they are coming from the data set. You remember I told you that since I have written right, and look at it here, because I have written right, where is right? Right is inside the data set called B. So before I actually can execute this, I need to write B $right. Okay. And before I write female, I need to write B $female. I need to write the name of the data in which they are coming from. So B $right, and then B $female. That's all you got to do. Okay. So please do that if you are following me. And then you now execute. And when you execute, you can see on the right here that the data is now showing nicely. So just by picture, using the box plot, you will see that, remember, the male is 0 and the female is 1. So you can see, look at the center, the average. You can see that the average of the female, yes, Hassan?
Sir, please, why is it that your plot side, nothing is showing?
Oh, you don't see my plot?
No.
Oh, sorry. Let me see.
I think including the first one to that.
Oh, you should have told me. If you weren't seeing that plot, you should have told me. It's showing now.
Yeah.
Yeah, the problem is that I don't know why with my R, maybe I need to update it. With my R, it's supposed to show in the, it's supposed to show in the actual plot. It's supposed to show under plot. Let me see. But you can see it, right?
Yes, for now, it's just the plot that is showing. The rest are not showing.
Yeah, I'll come back to it. I don't know why the plots separated themselves. So in this plot, you will notice that the male are 0 and the females are 1. And when you look at the female, you can see that the mean, when you check it at the far left, you see that they are higher than that of the male. So on the basis of this, just by picture, you can tell that it appears that the females are scoring more on writing than the male. But as to whether that is significant, we are yet to test it. Okay, so how do you test whether that is significant? Let's go ahead and go and show that. I'm back to my R command window. To check whether it is significant, we use, because we have assumed that the data is not normally distributed, we use Wilcoxon command. So you type wilcox.test. And sometimes when you put a cursor there, I will even tell you what it means. I hope that the description of what it means, you can see it in my screen. Do you see it?
Yes.
Okay. So you see, it says that it performs 1 and 2 sample Wilcoxon tests on vectors of data. The latter is also known as Mann-Whitney. So there are 2 of the Mann-Whitney, of the Wilcoxon. One is called Wilcoxon rank sum. That is a Mann-Whitney. And the other is called Wilcoxon signed rank. The signed rank is when the data is paired or dependent. The rank sum is when the data is independent, like we have in our case here. Okay, yes, Mami.
Prof, I'm sorry to take you back, but please, the box plot command, when I typed in my command and I ran, it's saying that there's error in the plot because the figure margins are too large. I'm wondering why I'm getting that feedback.
Yeah, if it says the figure margins are too large, it's possible that, is it showing on your bottom right here?
Yes, please.
Yes, so you just have to hold the corners here and just make it bigger, like I'm doing. Just hold the corners, make it bigger. Or that little maximize box, you just maximize it and it will show. And run it again, it will show well. Okay. So Wilcox.test, that's the command. How do you now check whether the female and male are significantly different or not? Well, the way to go about it is very simple. After you type everything, go and copy the same thing here. Copy the $, right, tilde $, female, just as it was before, and copy that into this test. That is when you are doing independent sample. Let me check something. Independent sample. What I'm doing is not independent. I just want to check whether dependent sample work. So dependent sample requires a new arrangement. That's what I'm saying there. So independent sample, that's it. You just have it as this and then you run it. Run what is you see here. And there you go at the bottom, you can see the result there. It says Wilcoxon rank sum test with continuity correction. So this is when you are comparing the writing score between male and female. Now, remember in your head, the graph showed that the females are outperforming the male, but you didn't know whether it's significant or not. To know whether it's significant or not, your p-value must be approximately 0. So when you come and check your p-value here, it's approximately 0. That's all you needed. All you needed was to check the p-value to be sure that females don't just outperform males when it comes to writing, but females significantly outperform males when it comes to writing. Before you can bring that word significantly, you must have checked the p-value and be sure that it is less than 5% or less than 1%. That is why sometimes when people talk and they are talking and they are saying there's a significant decrease, there is no significant decrease. You can't use the word significant unless you've tested it. So you don't use words significant. when you've not done a statistical testing. This is assuming that the data is non-normally distributed. That's what we use that. Okay, any question on this? So what would you have concluded? So it means that there's a significant difference in the male score and that of the female score. That's all we know of. Very, very significant. Very, very significant. Okay, let me try this. The command that I did earlier, that didn't bring the paired. I still want to try it and see why it did not show the paired. Maybe I need to write the full name of true. That's supposed to. Yeah. Now, for one to actually be able to show the paired, you got to kind of organize the data in a certain way. And it is after you've organized the data in that certain way before the data will allow you to be able to run the scores that you want to do. Okay. How do you organize the data? It's simple. All you got to do, let me see what I can show that. It's the lady who was asking earlier. I was trying to show you. I was trying to show you. All you have to do is that just have this the subject on the far left, then you have the MPG1, then MPG2. That's it. Don't have it like in the way we have it here in this data set. Okay? You have to kind of organize it separately. Okay? So this is a sample, and this is the next sample. Okay. But the one that we worked, you can see that the male and female are mixed together. They are mixed together. They are mixed together. And that is why this command nicely works. But for the paired, whether it's parametric T or non-parametric Wilcoxon, you are supposed to have it organized that way. Hopefully, when I get to more than 2 samples, I'll be able to show you an example of that. Okay, so I want to show you something now on the screen here. Let me show you this sample that you have on your screen. There are some assignments I'll be giving you to run some of these things all by yourself. Do you see the one on the slide? Do you see? Or the slide is not shown?
Yes,
It's showing, sir.
It talks about a random sample of salaries of some University of Ghana students and KNUST students. These are 2 different samples, okay? And you can see that the samples are unbalanced because the number of observations in UG are different from the number of observations in KNUST. So it shows that the sample is unbalanced. Now, without you being told, who can tell me this? Are the samples independent or dependent?
It's an independent.
Independent. Why do you say it's independent? Normally, when you don't know why, I knew you had to. Yes, Hassan.
Can we say they are 2 different?
they are independent because they don't have they only have 1 samples. Like especially for UG, it just has 1 sample for it, and then KUST 2 has 1 figures of samples for KUST.
It's independent because the salary of one does not depend on the other.
How do you make those statements? The salary of one
It's different because the subjects are different. It's independent because the subjects are different.
And apart from the subject, the one Hassan said, you can't only talk about the subject and go scot-free. You have to say that the subjects are different, but also what? The samples are also.
The samples are, yeah.
And guys, please distinguish between the subject and the sample. Because in another one, the subject will be different, but the subject will be the same, but the samples will be different. So it's important to distinguish between the subject and the sample. Okay. All right. So this one, you can test it and then come out with a result. Let's go to the next one. 3 samples, 4 samples, 5 samples, 6 samples, 7 samples. Okay. These are the ones sometimes we use for political parties, for multiple groups, multiple classes, and all of that. For example, you can talk about foreign companies, state companies, private domestic companies. You can talk about political parties, yeah, NDC, NPP, NPK, NDC. It's different classes, groups. In that case, you go beyond t-test and you go beyond Wilcoxon. You now enter into the world of ANOVA. ANOVA, analysis of, and the non-parametric version. Somebody is disturbing a lot. The person is not even aware. The non-parametric analog of ANOVA. Who can tell me? Who can tell me the non-parametric analog of the independent ANOVA? Remember, when you go to the 3 or more samples, you have to also know that you have dependent and independent. So when it comes to ANOVA test, we are going to be doing, you need dependent and independent. And then is non-parametric version 2, you need dependent and independent. So what is the non-parametric analog of the independent ANOVA? So independent ANOVA means you have like 5 samples. All of them are independent of each other in the sense that the subjects are different and the samples are also different. Ebenezer?
The age test.
Sorry?
The age test.
The what test?
The age.
What is the age test?
The Kruskal Wallis test.
Yes. So you should mention the full name, the Kruskal Wallis test. The Kruskal Wallis test is a non-parametric analog of the independent t-test. Guys, if you didn't know, please document it then. Now, what about the non-parametric analog of the dependent ANOVA? The dependent ANOVA. Dependent. So in this case, the samples are dependent. So the subject is the same, but the samples are different. What is a non-parametric? Because the parametric is called dependent ANOVA. What is a non-parametric? Hassan?
I'm trying to know, is it the Friedman test?
Yes, it is a Friedman test.
Okay.
It's a Friedman test. So guys, the thing is that when the story is told, you are supposed to determine these 4 different tests, which one you are going to use. The story is in such a way that you should be able to pinpoint which test you are going to use for what. It's very important. Okay. Now, when you are doing the ANOVA, let's go to the ANOVA, which is a parametric test for testing differences across 3 or more groups. There are certain assumptions that must come to play before you use the ANOVA. The data must be normally distributed. The samples must be random. There must be ratio data. The independent variable must be categorical. The dependent variable is always numerical. We know this. Even the one we just checked. The dependent variable is numerical. The independent variable must be categorical. So there must be categories, classes, groups. And then the variance must be homogeneous. Okay. So these assumptions must hold for ANOVA to 10. Now the ANOVA 2, they are different types. We have 1-way ANOVA, we have 2-way ANOVA, you have 3-way ANOVA. For example, in 1-way ANOVA, you can be checking the smoking status of people. Those who are never smokers, former smokers, or current smokers. So you're only checking their smoking status. But you can decide to check their smoking status against their gender as well. So you want to know a female who is a never smoker, a male who is a former smoker, a female who is a current smoker. So the categorical comparison are gender and smoking. And then you can have 3 comparison. Okay, gender, smoking, and beer consumption. A female never smoker, but consumes beer. A male, former smoker and consumes beer. A female current smoker and does not consume beer. You can have all of those categories. All right. So this is a table I just asked you a question from. And I'm expecting that you will all learn to master this table, because it's a very important thing. Okay. Let's go back to our data set that we have been dealing with. The data set that has the 200 students with different demographic information. Now,
hello, Prof.
Yes.
Sorry to take you back. Please, when you were explaining the types of the ANOVA, I remember we talked about the independent and the dependent, and there's various steps you can do about it. And then you mentioned that we have like 1-way, 2-way, 3-way. What differentiates between the types of classification? Like, I mean, which one is the 1-way, 2-way, 3-way? And then which one is the dependent and independent? Is it a type of test that can be done, which is called dependent, and the independent, classified as dependent and independent? And then, yeah, I'm not sure which classification will give you the 1-way, 2-way, 3-way.
As for the classification of dependent and independent, it's not even just ANOVA. It's every test, whether it's T-test, Z-test, all the tests, F-test, you have to check. The dependent and independent is about the sample. It's all about the sample. The sample in your hand. The sample, is it a sample where you are having the subjects repeated or the subjects are different? That's all.
Okay, so based on the sample, you can decide to do the Kruskal Wallis or you can do the Friedman as discussed. And based on what would you classify it as 1-way, 2-way, 3-way? Is it the types of the ANOVA that exist?
By the way, you're confusing some things. Okay? The Kruskal Wallis and again, you have to study this table. Let me go back here. You have to study this table. If you look at this table, the Kruskal Wallis is here. The Kruskal Wallis is a test, but it's just the non-parametric version of the ANOVA here. They're all tests. Now, when you use the Kruskal Wallis,
so those ones are more like tests. Okay.
Don't try to understand them all now if you don't know all of them now. You have to just go and start, because it's a classification with a lot of cross-tabulation. You have to just know that under ANOVA, have a situation where the data, the sample is dependent. Even under Kruskal Wallis, okay, under ANOVA, you can have independent ANOVA. And then under ANOVA, you can have dependent ANOVA. So the one I've highlighted here is independent ANOVA. But once you have independent ANOVA, it's non-parametric version, which I would have called independent Kruskal Wallis, but I don't have to call it independent Kruskal. Its non-parametric version is Kruskal Wallis. Okay, so what is the difference? The difference is that one assumes that the data is normal, the other assumes that the data is not normal. Okay, now when you enter the ANOVA is comparing, let's say you are comparing ownership of a bank. One is state bank, one is foreign bank, and one is private domestic bank. What are you comparing? Just their ownership. But somebody can say, hey, don't compare only their ownership. I also want you to compare their size as well as their ownership. So in this case, you're comparing based on ownership, and you're comparing based on size, where one is small size, medium size, big size. Okay. And that second one I just told is still ANOVA, but it is a 2-way ANOVA because the comparison types are 2. And you can have a 3-way ANOVA where you're going to compare their ownership, you're going to compare their size with the ownership, and then you're going to compare maybe their profitability with the size, with the ownership. Now, 3 different categories. And each one, you're comparing, each one, you have state, private, domestic, and then foreign. Under each one, you have state, private, domestic, foreign. So this is a cross tabulation. But I'm not going to teach you the other one, you know, where you have plenty, two-way ANOVA, three-way. Yeah. Once you understand the first one, those ones are simple. So you just need to sit down and know the distinction between the two. As for the relationship between ANOVA, independent ANOVA and Kruskal Wallis, one is parametric, the other is not parametric. But you also have dependent ANOVA, which is parametric, and then independent version. Dependent ANOVA and then independent ANOVA. The same way you can have Kruskal Wallis and Friedman. What is the difference between that? One is dependent, one is independent. The Friedman is independent, the Kruskal Wallis is independent. And then you have ANOVA. The first ANOVA is dependent, the second ANOVA is independent. Then you can have Kruskal Wallis and Friedman. The Kruskal Wallis is independent, the Friedman is dependent. Okay. But what is the difference between these two? Well, the ANOVA guys are parametric, the Kruskal Wallis and Friedman guys are non-parametric. The rest of any comparison that will come, the type 1, type 2, is only for ANOVA and nothing else. Okay. All right. So let's go to the data set that we used before. I'm going to compare the program type. Let me just go and show you the program type. So watch the Excel data set I'm about to show you. This is the Excel data type we have been using all along. And I want you to look at the far right column. When you get it, look at the far right column, column L. Do you see the program type?
Yes, sir.
You see the program type? Look at the different program types.
General vacation.
General.
Sorry?
General, vocation, and academic.
All right. So what does this mean? We are all going to write a test. And what is a test? Well, the test is that we are all going to write a test called writing. So still on writing score. In fact, I can even use a different one, but let me still stick on writing. Let me use maths. Okay, so we are all writing maths, and some of us are students who have specialized in general education. Some of us are students who have specialized in vocational. I mean, at the PhD level, you know you've all specialized, isn't it? So some of you are what? HR, some of you are accounting, some of you are finance, some of you are health services management, public administration. And so you have specialization. So here too, the specializations are vocation, general, academic. So some of them are specializing in academic, the pure academic thing. Others are doing vocation, others are doing general. Now, what I want us to do here is that I want us to check whether the type of program you do can help you to pass maths very well, mathematics. So we want to check whether there is a significant difference in math score, whether it is influenced by the type of program that you do. Guys, you understand what I mean? Okay. So on the surface, you might think that, oh, well, those that are doing academics should do well in maths, isn't it? Isn't it? I mean, just on top of your head, you might assume that. But we need to check. We need to check whether that is true. So that's what we are going to do now. Okay. So I'm going to take you to the R and then we'll check. So when I say these things, you have to write them down so that you don't forget. So we are checking whether there's a significant difference in math score, okay, relative to the program type. In other words, whether the type of program influences the score that you will get in maths. Let's go and see whether that is the case. So I go to my R studio, I'm leaving one line, and then I'm just going to, first let me do a box plot, okay? Let me do a bit of a box plot to see what is happening. So I'm going to do a box plot to see whether there's a bit of difference. So type box plot. Okay. And then the program type I'm using is mass. So I'll do $mass. And you must ensure that the name you are using is exactly the same name in the Excel. Okay. So when you type mass, then you do your tilde sign. And if you can remember the last column, the program type, I called it PROG1. Do you remember? So I'll do $PROG1. You see, sometimes when you start typing, it will show you what is in the data set. So in this case, it's showing me what's in the data set. Okay. Now this is a plot. I want to give it some color. Okay. So you can use any color, color equal to, and then I want to use a new color called Alice Blue. Alice Blue. You can use red, blue, green, yellow, black, anything. Alice Blue. And strangely enough, my pictures don't show here. That is what one of you have indicated to me. So I need to be sure why my pictures don't show here. There are so many things that appears I need to update. But I'll do that later. So I'm going to run this and show you the results. So let me go and show you the results. Okay. So at one point in time, some of you were not seeing the results. So confirm for me whether you see the results.
Yes.
Yeah.
Very good.
Showing now.
Note that these results, the samples are 3 different samples. And the average is the horizontal line in each box. Looking at the average, which group seems to be doing well in maths? Seems to be doing well in maths.
Academic.
Academic. Yeah.
Yes.
So
yeah.
now, with that at the back of your mind, we are going to test whether that is true. This is just a picture, and mind you, most of the time when what the picture is saying is what the test is saying. Okay. So let's go back to our command and just go and run the same thing. This time, ANOVA is what we are doing. Okay. ANOVA is what we are doing. How do you run the ANOVA? It's very simple. This is how you do it. The first thing you have to do is to type fit. And that's the name I'm calling it. I'm calling it fit, but actually you can call it anything. You can even call it a letter. Sometimes when you use single letters, it's good because I is not confused too much about it. So let me just disable annotation. All right. So you just write fit. You can use any letter, fit AOV. We are just writing the ANOVA command to just do statistical testing, whether truly academics are outperforming the others in maths. So you do B, that's the name of the data, maths, with a tilde sign, B program type. That's it. And then after that, you want the result. So you type semicolon. After that, you type semicolon, and then type summary. You type summary into brackets, the name you gave to the data, which was fit. So summary into bracket fit. I hope you guys are following me because I can't hear anybody. I hope you are following me. Okay.
Yes, we are.
I just wanted to ask a little question for clarification. Earlier, you mentioned that if we didn't want to use the $sign, we could just install the program.
No, you could just attach, not install.
Attach.
Yes.
Okay.
I said you could attach, but you should not forget to detach.
Okay. Okay.
Yeah. But now you can see that I don't want that same challenge, so I'm just keeping it at, bringing the $sign as I go forward. All right. So that's it. Once you've written, just click, look at the bottom, the results is going to show. That's it. Look at the bottom. You can see that the entire ANOVA table is showing down here. The most important thing is the last column, which is the p-value. The last column. Okay. The last column here is a p-value, that one. That p-value is what you're looking for. If you look at the p-value carefully, guys, it is approximately what number? What number is that? Okay, so let me just get, anybody?
0.
It's 0. Okay, what it means is that there are 12 zeros before the 736, before. So you write 0.00000012 together with this. There are 12 zeros before the 736. That's what it means. So it means that the number there, which is a p-value, is approximately 0. Okay. What is ANOVA testing? Let me show you the null hypothesis. The null hypothesis of ANOVA says that the mu for the first group is equal to the mu for the second group, is equal to the mu for the third group. I'm using 3 groups because in our case, we have 3: academic, vocational, general. Okay. The alternative says this. So what does the null is saying? The null is saying that there is no difference. That's what the null is saying. There's no difference in the means.
Yes.
The alternative is saying that mu I is not equal to mu j for at least 1. At least 1 I, which is not equal to j. Of course, in this case, we know that I or j is 1 to 3. It's 1 all the way up to 3. So what is the alternative saying? The alternative is saying that at least one of them is different. Remember, the null is saying that there's no difference at all. There's no difference, statistically, there's no difference between the score for general and the score for vocational and the score for academic. What he's trying to say is that if this one is 50, this is also 50, this is also 50. That's what the null is saying. But the alternative is saying that no. At least one of them is different. And if you have at least one of them, even if 2 are the same, but at least one of them is different, it nullifies the null hypothesis. Okay, when your p-value, we've said this multiple times, whenever your p-value is less than or equal to alpha, the level of significance, we reject the null hypothesis. We reject the null hypothesis. In this case, our p-value is 0. And this 0 is less than even 1%. Okay, so it's even less than 1%. Not to even talk about 5%. So what do? We reject the null hypothesis, which says there's no difference. We reject the null hypothesis that says there is no difference. And then conclude that there is a statistically significant difference in the mathematics score across those 3 different programs, general, vocational, academic. Among those 3 different programs, when it comes to maths, there's a statistically significant difference in the sense that academic are earning the highest. And, you can talk about it. If you want to find the means and all of that, you can do that. And then you can see the mean. But then the graph showed us. The graph showed us that academic are scoring a lot in mathematics, followed by, I think, is it general before vocational? Okay. So that is what ANOVA is doing. ANOVA is telling us the group dynamics. But what ANOVA is not telling us is, okay, now you've told us the one that is the highest. But what about between each one of them? What about between vocational and general? What about between academic and general? What about between, suppose the groups were 10. What about the differences across 1 by 1, 2 by 2, each pair, each multiple comparison? You can use something known as Tukey multiple comparison test to do that. Okay, and you can do that. By the way, doing that Tukey's multiple comparison is something you can do it on your own. But what I've just done is that I've shown you how independent ANOVA is done. You can do the same thing with dependent ANOVA. Okay, you can do the same thing with dependent ANOVA. When you arrange the data and then you bring what? Paired. Okay, when you rearrange the data and they are not vertical, but they are separate. Okay. Then you can now do the dependent ANOVA. But here too, I can do the Kruskal Wallis. Did you know that? Suppose I know that the data set is not normally distributed. If I believe the data set is not normally distributed, if I believe strongly the data set is not normally distributed, I can make the assumption and do the Kruskal Wallis test. How? It's very simple. Let me show you. Instead of writing, just a second. Okay, so just let's continue. So what you want to do, if you want to do the Kruskal Wallis, all you have to do is type Kruskal dot test, and just everything that you had here. Put the same. Please, when will you do the Kruskal Wallis test? You will do the Kruskal Wallis test when you are assuming that the data is not normally distributed. Yeah. The one that we have here, we have assumed that the data is normally distributed. But if the data is assumed not to be normally distributed, this is what you do. You do a Kruskal Wallis using this command. Okay. So you do Kruskal dot test and just run it. Okay. Let me show you that one down here. You see the results down there. You see you have Kruskal Wallis rank sum test. And that one to the p-value is what? Is 0. And because I want to the p-value is 0, it is just supported. If the data is not normally distributed, we will still say that the program type affects the scores. The type of program you do does affect your mathematics score that you have. That's what we would have concluded. Okay? Because those who are doing maths, those who are doing academic will do better than those who are doing general, and they too do better than those who are doing vocation. So even though the data is not non-parametric, the non-parametric result is confirmed, okay, for the data. Yes, Felix.
So if I assume that the data is not normally distributed and we perform the Kruskal Wallis test, what on the results will show that actually the data is not is normally distributed as we assume it not to be normally distributed?
Oh, I think if you were in class last week and this week, you see that there are so many ways we used to test them. So we test. One of the things is we use the Shapiro.Welk test. We use Anderson-Darling test. We use several tests, and I showed you last week, and even on Monday. So all you have to do is to test it. If you test it and it says the data is not normally distributed, then you know. And sometimes you know it ahead of time before you started your work. If most of your collected data is ratio, you know it's normally distributed. If you are picking a lot of ordinal data type, then you know it's not normally distributed. Yeah. So it's simple to test it. Yes, Bernice.
Can the scatter, the box plot will give you an idea whether it's normally distributed or not?
No. The box plot is not used to determine whether it's normally distributed, but there are other plots which I showed. You can use histogram, you can use kernel density estimation graph. You can also use the quantile normal probability graph. I showed that. And then there is another graph you can use. What is it? You can use histogram. Yeah, I've mentioned histogram. Histogram, quantile normal probability, and then kernel density. These three are enough to tell you whether the data is normally distributed. But even if you use a graph, you have to test it. You have to test it by using the Shapiro.test to confirm the graph. Okay. So I've just shown you all the tests. The ones I couldn't show you are those that are paired, that are dependent, which require that the data is just arranged nicely. Okay. One on the left of the other, one on the right of the other. Okay. So, and let me show you this in the slides. So when you look at this slide, please, do you see the slide?
Yes, please.
Yes,
so this is what I mean by the data must be arranged for you to use dependent, samples or anything. The data must be arranged like one is arranged to the other like that. One is arranged to the other like that. That way you can now plot it. You can now take it to the R and you can attack the same thing that we did all. The same command. You just do a comma, then you write paired equal to true. And that will test for the dependent samples. That will test for it. But it must be arranged like this. Okay. So these are the same thing, but it's just that the subject is the same, but the samples are different. So this means that lettuce in the store A is priced at $1.17. Lettuce in store B is the same lettuce in store B is priced at 1.78. The same lettuce is priced at it. So the same thing, but it's being repeated, in several stores. That is what it means. So try the rest I have in the slides, and then you can look at it and then have a feel of everything. And then you check the interpretation. I have them all in the slides for you. Do all of these. The Friedman is a paired non-parametric test, dependent, okay, dependent. And I have an example of that also here that you can look at. If you look at this one, okay, you have RMBA, weekend MBA, executive MBA, and the samples are unbalanced, but it's an independent sample. Okay? And so you will use, you don't need anybody to come and tell you whether it's dependent or you got to look at it. Okay? If you look at this one, clearly it's an independent sample. And so you will use independent ANOVA to do it. If you compare with others, you will see that is the reason. But when you look at this, you look at the one I showed you earlier, this one here, when you look at this one, you see that the groups are 4, okay? But even though the groups are 4 and the sample is 4, the subject is the same. And so it's not an independent, it's still dependent sample, but the samples are 4. Okay, so you use repeated ANOVA or dependent ANOVA. If the data is non-parametric, then you have to use the Friedman test for it. You got to master these things. Ladies and gentlemen, that brings us to the end of the entire caboodle.